Hello, everyone. Thank you for being here. The question I would like to ask today is how robotics can help us to make the world more sustainable. How can it make us live better? How can it make us to protect the environment so that we can give this world to our children in a sustainable manner? Now, sustainability, robotics, physical AI, it's everywhere, it seems, but I don't think it is. It's mainly in the media, and not yet are robots used in our everyday lives. They're not really in our homes yet. They're not yet in the environment, and they're really not yet used for environmental and sustainability-related applications. So I've spent the last 20 years of my life trying to imagine how we can create the complex idea of something life-supportive, a technology that can really help all of us and manifest it in the physical world. Now, I hope that today I'll be able to share with you a few of those examples of robots we have built and how they can address the UN Sustainable Development Goals. What you see here is our new robot. No, actually it's not. It's a V, but in many ways it's the holy grail of robotics. And if you think about these animals and natural systems, how they operate, we see that they're not just an algorithm embedded in a physical dead body. They're really complex in integrating the intelligence in the brain, in the body, in the materials. In fact, if you look at that, we see that they use a lot of sensing, control, navigation, the vision systems, the antennas, the brain, but also they combine this with complex aerodynamics and also complex materials, structures, actuators, and the morphology. So the physical body is equally important as is their neural system, as is their learning process, and this enables them to operate and live in the outdoor complex environments. Now we looked at that and we wrote a paper trying to outline how intelligence can be thought of. So we can think of intelligence as being about control, sensing, and planning. And if you have a robot that flies and, let's say, wants to land on a wall, we can do a lot of this using classical AI frameworks, as they are known, neural networks, control methods. But what we see is when we scale down scale down the robot, and we have, let's say, animals that are at the mass of a few grams or milligrams, they cannot necessarily use the complex sensing and weight of these sensors. So they rely increasingly on the physicality, on their body, to help them in the motions. For example, the flies, as they want to land, they use their legs or they use their antennas to align physically to the surface of the wall. Now this we can call mechanical intelligence, or also it's called embodied intelligence or morphological computation, where the morphology, the body, does the computation for them. I think if you want to create truly intelligent physical AI and robotic systems, we have to do both. We have to understand and develop the materials, the structures, the morphology, but also the control systems that enable them to operate in the environment. So it's not one or the other, it's both. Now, at EMPA and the EPFL and also with Imperial College, we develop exactly that. We try to innovate on the material side, on the design, but also on the control and autonomy to create a Swiss Army knife of environmental sciences, where the robot is the tool, the method, the extension of the human to really help us augment capability and create a resilient world in climate monitoring, forest health, aging infrastructure, assessment and repair, climate water assessments, biodiversity monitoring, and so on. So I'll give you a few examples for each of those environments. And I think a key element is how to master the environments. How can we make robots that deal with earth, air, fire, and water? How can they operate in those environments? And what is the value that they can bring? So let's start with air. Now in air, we have this concept of robots distributing sensors that deploy and glide through the environment, sensing the environment while reducing the impact to the environment. So these are systems that are fully biodegradable, where the materials are bio-integrated, where we can close the life cycle and have robots that are deployed, then biodegrade in the environment, while providing the capability in agriculture, forestry, and so on. And this is what we design, which is the transient robotic life cycle. So we build a robot, we use it, instead of throwing it away, which today 99% of robots are being just basically put into landfill. we want to make it biodegradable and then potentially regrow to heal the structures and develop the robots that they are fully integrated, really like an artificial living system. So an example you see here. Let's say we have a drone that can fly and then wants to place a sensor on a tree or in an agriculture context to measure the environment, measure the temperature, light irrigation, pH levels, biodiversity, nutrient needs, water stress. We can do that by placing it, like as you see here, with a dart system that then places it on the tree. Now this dart, of course, needs to be, as I said, biodegradable. And to do that, we look at biohybrid cryogels, which are composite materials that use cellulose materials together with starch or agar or gelatin matrices, which can be molded into structures, then freeze-dried, allowing us to create very structurally strong materials and structures that have certain biodegradation properties. So we can design the life cycle, we can design the death of the robot. We make it functional as it needs to be, but it has a predefined end of life, which then is basically dying without leaving waste, e-waste in the environment. Okay, a second example is water. So how can we build robots that move in water, but not just in water, also in air? So how can we make aerial aquatic vehicles? And this is something we work on for about 12 years now. We call this the Proteus drone project, which is inspired from Proteus, the multimodal Greek god. Basically building robots that can fly, dive into the water, fly out the water, and also sail on the water surface. So multimodal aerial aquatic vehicles. We also wrote a book on that, and I would just like to show you one example of a robot that we built. So this is a vehicle that basically flies, they can land on the water surface, then reconfigures the wings into sails. The sails then operate to move on the water surface and measure the water properties and biodiversity. This allows them to autonomously move in complex environments inside of laboratory, but also in lakes and marine environments, accessing areas that are hard to access otherwise. So the key here is the energy efficiency. So we use the sailing as a form of saving energy. Like this, a drone like this can operate over many kilometers without using precious flight energy or battery energy. So having energy efficient motion, the capability to transition between air and water really is a step change in the capability of the robotic sensing tool or monitoring tool. So how we think of that is that we build a new concept, let's say aerial aquatic vehicles, so they don't exist, so you cannot buy that. We develop it, model it, develop in the lab, and then use it for outdoor experiments to measure, for example, the biodiversity as you see here. So we take the sounds from the environment and then use an AI algorithm to identify the bird species and biodiversity in the environment. So it's a quantified measure of the environmental biodiversity using a novel robotic tool, allowing us to get new insights onto the biodiversity and the environmental properties. This helps us to protect the environment. This helps us to create policy to address biodiversity and water health. But to do that, we need the data. We need quantified data. We need the evidence. So how can we get the evidence? It's today not there. Robotics can be a tool to get there. Okay, the third example is fire. How can we make robots that fly inside of fire? And of course, it seems challenging, but we worked on that, looking at ways how we can build new materials, building this fire drone system that can fly and operate at very high environmental temperatures. New aerogel. Aerogel is a material used in space applications for very heat resilient, has very high heat resilience. So with this materials, with the new cooling system, with the special morphology of the robot, allows us to test them and operate around fire in very hot environments to do forest fire monitoring, assisting for firefighters in their urban operations, but also in inspecting high temperature ovens and chimneys in industrial facilities. Now, we did that and there was a lot of interest from industry, so we have now created a spin-off on this called the Fire Drone, which commercializes that for industrial applications. Again, the value is in removing the people, the humans, from the danger zones. Firefighters are heroes of our world. They're putting their lives at risks to save people people in industrial facilities also go in areas which are very dangerous, very hot, very hazardous. So I think we have an ethical responsibility to create robots that augment their capability, that remove them from the danger zones. Fire drones and similar systems is an example of that. Good. The last element is the Earth. So how can we shape Earth? How can we build robots that fly and then operate with Earth? Maybe 3D print structures in space collectively to then build habitats, build and repair environments using materials that they can deposit from their body. So these are basically flying 3D printers that can deposit material from flight and like this augment the operation at height, because at height it's very dangerous for the people. A lot of injuries and deaths in the construction sector happens at height. So we work on this for about 10 years, and one of the robots you see here, which is a flying 3D printer, basically flying and depositing materials from flight, making layers of materials, and like this 3D printing structures to do sustainable manufacturing, sustainable construction. Now, this is a proof of concept, but the framework of high-precision surgical interventions in infrastructure, I think, has a lot of a lot of application potential in industry. One of those examples is repair of infrastructures. For example, here, doing pipeline repair, where the robot can deposit with very high precision of few millimeters materials to repair damages on pipelines, corrosion on storage tanks, bridge repair, and so on, like this, removing the need for humans to work at height or reducing the reliance on human operators in those environments. Good. In summary, sustainability robotics has a lot of applications from sustainable infrastructure, sustainable construction, forestry, agriculture, water health, Arctic exploration, extreme environments, and aging infrastructure. So all of this needs physical AI, needs robotics, and needs new opportunities in those spaces. So a lot is not developed, and we really have to innovate on that. So how do we innovate? I think we innovate by combining our expertise, doing meetings like this, combining together from policy to politics to environment, economy, industry, academia, and also investment, to really create a community that can support a new vision of how sustainability can be supported with robotics. And this, I think, is the fifth element, the element in between, the element today in the room. And one paper we wrote in 2020 was on physical AI, basically how we can define the skill development in physical AI. How can we develop a new generation of engineers that thinks in a multidisciplinary manner and can develop and manifest those systems. So we're now teaching also a course at EPFL in Lausanne on sustainability robotics, trying to train the next generation on to also how to make startups in this field, how the value proposition can be framed, and how the economic value can be then captured through these companies. And one of the core elements of this is the access to infrastructure. So how do we need, what laboratories do we need for that? And there's a lot of indoor flight arenas, where we can test robots and drones. There are a lot of outdoor environments, but really there's a gap. The gap is infrastructure where we can test and validate the ideas, but that represent outdoor real-world environments, but are instrumented and safe like indoor environments. And this is something that we have built, which is called the Drone Hub. The Drone Hub is based at the Nest building in Zurich at EMPA, and it has 3 innovation elements. So it's basically a caged structure where we can implement different industrial use cases, for example, from facades for 3D printing and repair, where we can install different facade elements or vertical gardens and things like that. And also a biosphere, where we can test biodiversity monitoring, agriculture use cases. And also the facade itself, where the robot can integrate with the facade to do a variety of autonomous sensing and interaction tasks. So the Drone Hub is an example of how such infrastructure can look like. We also basically look at that for system validation, project visibility, long duration tests through different partnerships, industrial collaborations, and public-private partnerships. So we are framing this and growing this really also as a community around this field. A second infrastructure that we are building now, it's called the Aero Aqua Arena. It's also in the Nest, next to Nest in Dübendorf, next to Zurich. And it has an outdoor caged environment and also an indoor large testing space. The space is quite large, it's 35 meters long, so more than 5,000 meters cubed. It has a motion capture system, so 42 cameras that can observe the motion of the robot. And also we are building a large pool in the middle of the space to test the aerial aquatic robots. So this is already used for robotic testing today, and it's going to be expanded further to really make it accessible for all of European research, international research, to really test and validate the robots there, with our help or without, just to have the environment, have the access, easy access to those environments for industry and partners to make impact. Another idea, third level of infrastructure, is to make mobile infrastructure robotic. And here is what you see here is the Forel. The Forel is a research vessel by the Forel Heritage Foundation, which is operating around the fjords of Greenland and going to the South Pole as well soon. And from there we are testing our new robot, the Medusa, which is a robot that can land and then deploy a robotic underwater tentacle to do water monitoring and inspection and sampling tasks. So we've gone to Greenland last August and deployed this robot from the Forel, making the Forel as a deployment platform that can access environments that it typically could not, such as going close to the glaciers, close to the floating ice, close to the icebergs, because it cannot go further than that, right? But the glacier is a kilometer from here. So how do we measure the biodiversity? How do we measure the environmental conditions in those environments? And so here you see the Medusa being successfully deployed, being, to the best of our knowledge, the first aerial aquatic vehicle deployed in Arctic waters. And we successfully retrieved samples from the glacier melts that were melting into the fjord. So this gentleman holding this sample, and we are now looking into the biodiversity of that with the hope to create and find new life, which can help us identify new enzymes, new medication, new antibiotics, because these organisms live in those extreme conditions. So there's a real potential for also transformative human health solutions coming out of those samples. We are now also going back to Greenland this year, then next year to the Arctic, to the North Pole with the Tara Polar Station, making those platforms a robotic tool for environmental monitoring. So we also have now a competence center which combines the expertise and is a platform for international collaboration. And yeah, one thing to mention is the new 20 francs of Switzerland. And you see here, see the Nest building, which made us very happy. So that doesn't mean we get any of those coins. But to come back to the financial offering, I think sustainability robotics can address many sectors, from manufacturing, inspection, to supply chain, to healthcare, home care, agriculture, food safety, food system, and also water health and safety. So these are the relevant topics we really need to innovate and create new solutions together. And I think the most important is that we don't think of us as being isolated, but we really need to create a platform for also international impact and working together internationally, sharing our privilege that we have today all together in such a beautiful venue, but also in the research ecosystem we have in Central Europe. Thank you very much.